parts per million, so I don't have a scale bar on here. And the sample return sites are plotted in black symbols here. The Apollo are squares, obviously. And you can see that these are all within this sort of red high region, which has been termed the Procol creep train due to its enhancements of these rare earth elements and other associated incompatible things like that. And so the idea is that the Apollo samples may not be representative of the bulk crust, for example, things out here distant from this near-side enhancement of thorium. And that the meteorites, because they're a result of a stochastic process of impacting the lunar crust, could represent a more diverse, broad sampling of the whole lunar crust rather than just this anomalous near-side region. Yeah, the problem with them is that we don't really know where they came from. We can say very generally, okay, they came from the moon, they came from Highlands, they came from Mars, but beyond that, there's not really a whole lot we can say. So the idea behind this project is to measure them very carefully in the lab and sort of start seeing if we can use reflected spectroscopy to lay the groundwork to start pinning that down with remote sensing. So just very quickly, these are the samples that I have been working with. So I have basically 2 samples from each type, if you will. I have 2 feldspathic breccias, which are very beat up, as I'll show you some images in a bit. 2 unbrecciated basalt samples and 2 fragmental basaltic breccias. And these are actually paired samples. So they came probably from the same event on the lunar surface, so it should be very closely related. As I said, the motivation for this is that modern remote sensors are able to detect very subtle differences between reflectance spectra across the surface. So they really should have the ability to detect the subtle differences that enable us to pinpoint compositional subtleties that we wouldn't have been able to do with previous remote sensing missions that have only a few bands. However, lunar meteorites, they're kind of a mess, especially these feldspathic breccias. They're complex and jumbled up, basically as far in as you want to go. As far as you can zoom with your backscattered electron, these are just kind of a mess. You can see very large, distinct clasts. For example, these are feldspathic. This is more mafic. These are backscattered electron images. So the brighter things tend to be dominated by heavier cations, iron, calcium, things like that, whereas darker regions are more dominated by feldspar. This is an example of one of the feldspathic breccias. So this is kind of the worst case as far as my samples go. But they do have some pretty neat things. This is an example of highly exalted pyroxene, which just, and the quadrilateral doesn't come through too well, but these are they're extreme ranges in composition. These are outliers in this sample. These are the most extreme pyroxenes that I analyzed. There's kind of it's not even showing through the actual compositional window, but it goes something like this. And these guys are extreme outliers here, and it's very coarsely exalted. So there is some very interesting stories to be told in here if we can just unravel these and get at them individually. But doing that in a bulk sample form is exceedingly difficult as far as reflected spectroscopy is concerned. So, as I just said, they're kind of mixed up and jumbled up. The geologic context of the whole stones is not really all that meaningful, because they're basically this amalgamation of various different components that get glued together and ejected off the surface in the form of a meteorite. What we really want is where those specific components came from, what the context of those guys is. Say a big troctolite class. Where does that tell us? So what we really want is to be able to measure the actual components of these rather than just looking at the bulk samples. And that's easy in some cases, less easy in others. This is the most simple sample. This is the one I've worked with so far. This is the MIL, unbrecciated basalt. And I'm going to step through these next few slides and sort of increasing level of complexity of these samples. This would be, I would classify as relatively easy to do this for. The last one's much less so. So this is another unbrecciated basalt. This is LAP. You can see beautifully zoned large pyroxenes in this guy, as opposed to the exalted pyroxenes that I showed you previously. This is one of the basaltic breccias, and you probably can't see this, but it has very fine exsolution features in the pyroxene grains. Yeah. But it does have some fairly glassy matrix stuff that's going to be a challenge. And then lastly, the feldspathic breccias are just a complete mess. They have a very large panelizing class. This one down here is a troctolite class, which is something I would be really interested in getting my hands on and analyzing directly, but it means getting it out of all this other stuff. So this is something we've just begun to do. This is something I'll be continuing to work on. over the next year or so. These are spectra I've measured of the bulk samples, and you can see that a lot of them have this kind of pronounced negative continuum slope. That's because we measured them as chips rather than as colors. And over here on the right, I'm showing you spectra of the components of that. Miller Hills, the ungranulated basalt, the first example I showed you in the previous slide. I'm showing you a pyroxene separate and a contaminated, of course, the mescalinite separate, and then a comparison of an iron-rich plagioclase in the green, just for comparison. And then, of course, in the black is the chip measurement, which is over here, this blue one over here, this next spectrum. So once we've measured their components, what we want to do is actually quantify those absorption features with the modified Gaussian model, because it enables us to really get a specific control on the actual properties of these individual absorption features, which is what we'll be using to compare them to results from remote sensing. So this is a deconvolution of the pyroxene separate spectrum. For example, it has, I'm using two pyroxene absorptions here. You can see in the blue and the red. And the fit is pretty good. There are places where I'm not totally happy with it. For example, here at 1.2 and in the center of the 2 micron region. But this is an example of the sort of work that I've been doing and will be continue to be doing to do with these meteorite samples. How are we doing on time, probably? Okay. So the last topic is water, and I'll go through this quickly. This is relevant in terms of the recent discoveries of widespread water across the lunar surface. And these are the two of the images I showed you back at the beginning. One basically showing you that there are enhancements of surface adsorbed water, surficial water on the lunar surface near the poles. One of the projects I was involved with several years ago, very soon after I arrived at ground, was trying to, when we measured lunar soils in the lab, they always seem to have these weak absorption features here at 3 microns, which is diagnostic of water. We've always assumed that that's adsorbed terrestrial atmosphere. All these soils are dry, the moon's dry, you expose them to the atmosphere, boom, water gets adsorbed and you can't get it off. But what we wanted to do is to heat them up and see if we could get rid of that, see if it's just simply loosely adsorbed water, and if we could get spectra of these things without that component. And just talking about my results quickly, what we were able to do was to remove some of the water through heating experiments, but not all of it. I'm showing you 2 runs, sort of, and the temperature is coded by color here. So the hottest temperatures are sort of orange and red. And even by heating up to 400 degrees Celsius, we weren't able to get rid of even close to all of the water. There's less. You see Darby shaking her head, yeah, of course not. So, and this is not something that's just quickly. So this is, in the middle here, I'm showing you what happens if you take the sample out of the furnace and sort of let it sit and measure its spectra continuously. That you do see water coming back on, but not all that quickly. So this is probably not just simply adsorbed water. And I'm not a physicist, I'm not a sort of surface, this is not my area of expertise by any means. But this is just sort of a quick project we did. And really what it is, to me anyway, a lesson in publishing things quickly before somebody goes on and does the next thing. Anyway, so with that, I will say thank you. I'm not going to try and list everybody because I have to thank everybody in this room and then some. So thank you all for your attention, and sorry for the difficulties at the beginning. I'm happy to take your questions.
We'll entertain a few questions.
In your olivine section, can you go back to the spectra with the different olivine compositions? The 4-stroke 48, it didn't look like it had so much of the M1 piece. Is that just because there's no iron in those sites? Or?
Well, so this, what happens is actually this guy actually gets a little bit stronger over here. Maybe if I go back to that. Okay, so this is a very magnesium-rich olivine, and when you add more iron, this absorption, they move, but the relative strengths actually change. So the shape of that composite absorption feature will actually change somewhat. So it'll go from looking kind of sharp like this to looking more bowl-shaped like that one. The other problem with that one is it's sort of a coarse grain sample, so there's probably some saturation of the absorption features, which is confusing things as well. But that's, does that answer your question? I'm not sure if actually.
Other questions?
I can go ahead.
Okay.